Hey there, stats enthusiasts. Welcome to another lesson in Unit 1, Exploring One Variable Data for AP Statistics. I'm Goldie, and I'm here to take you through Notes 9 today, which is going to be all about standardizing z-scores and introducing the standard normal curve. So we're going to have a lot of fun today. Make sure to grab your notes, get settled in, and let's get started on this content together. So let's first talk about standardizing, okay? So I want to pose a situation for you. Let's say that we have our friend Mallory. She took a physics test and she got an 86%. When you get your test back, you want to know, how did you do, right? So if you got an 86% back, what would be your first question that you would ask about that grade? Well, you would want to know, okay, relative to the class, how'd you do? Because if the class mean was a 97, did Mallory do well, right? So if she got an 86% and the class mean was 97%, did she do well and why? Well, no, she did not do well, right? Relative to the class, because her score was lower than the mean score. So she would say she did not do well with that 86%. But what if she was told that the class mean was a 62%? Then would your perspective on the 86% change? It would. You would be like, okay, Mallory, you did well. Relative to the class, you scored an 86%, which is higher than the mean score of 62. So even though the grade was the same in both of those situations, whether or not she did well, we compared it to how the rest of the class did and specifically what that mean was. Now, when we ask, relative to the class, how did she do? We are looking at an observation in relationship to the mean. And it's one of those relationships that is asked so often that we actually have a mathematical procedure for it. We want to calculate how far an observation is away from the mean of the data set that we got it from. And this idea is called standardizing. And it's the process of counting how many standard deviations above or below the mean a certain observation falls. So you can see standardizing has the word standard in it. So you can think of like standard deviations, right? I want you to keep that in your mind here. Okay, so let's go back to our physics test that Mallory scored an 86% on. The following test, she actually scored an 82%, okay? Which was the more impressive score? Well, relative to herself, 86 was the most impressive score, right? But when you look at two different tests, we know that, okay, one unit might be harder than the other unit. So really a better judge of how well did Mallory do or which was the more impressive score, a question like that would be better asked by observing, okay, where was that 86% in relative to the rest of the class, and where was that 82% relative to the rest of the class? And having that information would allow us to answer the question about which is the more impressive score a little bit better, okay? So we use standardizing when we want to observe that distance, okay? When we want to compare two things, like in this case, Mallory's two tests, when they have a different scale. Now they're measuring the same thing, but they have, we call a different scale because the class did different on each of those tests. Again, due to a number of factors, right? So let's say on the first test, Mallory scored that 86%. The class mean was an 83%, and the standard deviation was 4.5%. Okay. And then on the second test, let's say Mallory scored that 82%, but the class mean was a 78%, and the standard deviation was 5.2%. Okay. Remember, standard deviation is the measure of the typical distance, and observation is from the mean. So if we subtract her scores from each of her means, that tells us the distance from the mean. But to determine if that distance would be considered typical relative to the rest of the class, we want to actually divide by the standard deviation. We want to divide that distance by the standard deviation to see how many standard deviations away from the mean it actually is. Okay, so the resulting number of that calculation is representing how many standard deviations away from the mean an observation is. And we have a special name for that measurement that's called a z-score. Okay. So let's look at this with our numbers, right? Because that's the words of it. Let's look at numbers. Okay. So the first physics test, our z-score, we're going to get by taking the observation, which is Mallory's test. We're going to subtract the mean to get the distance of that observation from the mean. And then we're going to divide by the standard deviation. So we're going to take her 86%, we're going to subtract 83, and we're going to divide by 4.5. Now, all of those three measurements are all percentages, right? Because we're all measuring a percent of what she got on the test. So when you do this calculation, you do want to make sure that those three values are the same units. Okay. And if they're the same units, then you don't really have to label them. Like I didn't change these to decimals from percentages just because they were all in percents anyway. Okay. So 86 minus 83 gives me 3. And then I take 3 divided by 4.5, and that gives me 0.67. So my z-score was 0.67. And what that means, because you're going to have to be able to interpret these z-scores, what that means is Mallory scored 0.67 standard deviations above the mean, okay? Because her 86 was above the mean, so that distance is positive when you subtract them. We have a positive difference. And then when I took 3 divided by 4.5, I got 0.67. So she is 0.67 standard deviations above the mean. That was her score. Let's compare it to the second physics test. We're going to do the same calculation, just different values because we have a different data set, right? So we have 82 now on our second physics test. We subtract 78 and we divide by 5.2. That gives us 0.77 as a z-score. And a 0.77 means that Mallory scored 0.77 standard deviations above the mean, okay? So with both of those tests, she scored above the mean. Now, which one was more impressive? Well, that depends how far away it was relative to the rest of the class. So yeah, we could take the difference and find, okay, on the first test, she was 3 percentages above. On the second test, she was 4 percentage points above. But really to see what was more impressive, we need to think about how spread out were those original observations. So that's why we bring standard deviation into it, okay? But now we're able to answer this question. Which was the more impressive score? Well, it was the second physics test, actually, because she scored more standard deviations above the mean on that test, okay? Because remember, you're in a normal distribution, you're centered at the mean, and the more standard deviations out you are, the farther away from the mean you are. So if you have more standard deviations above the mean, that means you're scoring higher relative to the rest of your classmates. So the second physics test was the more impressive score. Okay. So z-scores, let's define this then, okay? Because we're going to be using z-scores so much in this course, okay? So let's lay the foundation right now. If X is an observation from a distribution that has a known mean and a standard deviation, so mean would be mu and the standard deviation would be sigma, the z-score is going to be z equals x minus mu divided by sigma. Okay? X minus mu divided by sigma. So the interpretation of a z-score tells us how many standard deviations from the mean an observation falls, and it's also going to tell us in which direction that observation falls, right? Because observations that are larger than the mean are going to have a positive z-score, because that difference is going to be positive. But if an observation is smaller than the mean, it's going to have a negative z-score. So a positive z-score means you scored above the mean, and a negative z-score means you scored below the mean, okay? So let's look at, I think I have 3 examples here. We're going to look at just finding and interpreting z-scores before we take z-scores and apply them to our normal distributions, okay? So for number 1, female shoe sizes are approximately normally distributed with a mean of 8 and a standard deviation of 0.75. Find and interpret the z-score of a female with a size 6 shoe. Okay. So first we'll start off by what we're given in a problem, right? Standard math practice is to list what you're given. With symbols, we have mu equals 8 and sigma equals 0.75. Okay. Let's find the z-score. It wants us just to find and interpret it. So there's my z-score formula. It is actually given on your formula sheet for AP Statistics. So we're going to take our observation of a size 6 shoe, subtract the mean, divide by the standard deviation. So we get negative 2.67 as our z-score. Okay. Now we got to interpret that because it's not enough to just find it. We got to be able to use it or interpret it. So what this says is a female with a size 6 shoe, sorry, that should say shoe, not show. Shoe is 2.67 standard deviations below the mean shoe size, okay? Because it was a negative. So she was below the mean and she was 2.67 standard deviations below that mean. Okay. Next, if Corbin scored an 1100 on the SAT in 2020. The distribution of SAT scores in 2020 was actually normally distributed with a mean of 1083 and a standard deviation of 194. He also took the ACT as well and got a 23 on that, and we're told information about those ACT scores in that year with a mean of 21 and a standard deviation of 1.62. So 2 standardized tests, different scales for both of them. And the question says, on what standardized test did Corbin score better on? Okay. So again, this is a good example of how you could find the distance, right? You can see that he actually scored above the mean in both of those tests, but which one was better? Because they're not on the same scale exactly here. They're different scales. So how do we know which was more impressive? Well, we can standardize those scores, find the z-scores, and then compare the z-scores because the z-scores are able to be compared. Okay, so here's the information we're given for the SAT and the information we're given for the ACT. So you got to be careful about picking and filtering that information from the problem. But on the SAT, that's what he had. So we're going to find the z-score first for that by taking his score minus the mean divided by the standard deviation to get 0.09 as our z-score. And we're going to do the same thing with the ACT. His score minus the mean divided by the standard deviation, we get 1.23. Okay? So now we compare the z-scores, which one was better? Okay? Well, because the z-score for the ACT is higher, that means he scored more standard deviations above the mean on the ACT. So what standardized test did he score better on? The ACT. Okay? All right. So the third problem is actually going to lead us into our next topic here, okay? Let's see what we have. It says, on a typical school night, students get an average of 7 hours of sleep with a standard deviation of 1.2 hours, okay? I hope that's true for you guys, all right? Assuming this is a normally distributed set of data, sorry, that information got cut off. Assuming this is normally distributed, if Miguel got 8 hours of sleep, find and interpret his z-score. Okay, well, okay, let's find it. Miguel, he has 8 hours. We subtract the mean divided by the standard deviation. He got 0.83 as his z-score. Interpreting that, we say Miguel was 0.83 standard deviations above the mean hours of sleep, okay, of students, right? Now, we can take this and we can say draw the normal curve and approximate Miguel's location in that normal curve. And then we can use that to try to answer the question, he got more sleep than approximately what percent of students? Okay. Well, we've done these problems before where we draw the normal curve. Remember, we center the mean in the middle. So we got 7 hours right in the middle. And we go out 1, 2, and 3 standard deviations out on either side. So we've drawn distributions like this before. Now, where does Miguel fall? Well, he was 0.83 standard deviations above the mean at 8 hours of sleep. So where is 8 hours of sleep? That's about right there, right? 8 hours, 0.83. So you can see how it's not a full standard deviation above. A full standard deviation above would be 8.2. He got 8, which was a little bit less. So he's at 0.83 standard deviations above the mean. Now, he got more sleep than approximately what percent of students? Well, we know from the empirical rule, right, that this is anything less than the mean is 50%, and anything less than 1 standard deviation is 84%, right? Because we know, like, right in here is the 34%, right? We've done the empirical rule at this point. So we know, okay, he got more sleep than approximately what percent of students? Well, between 50%, 84, probably closer to 84%, but we're actually just not sure. right? It would be a complete approximation, and even that more of a guess, right? Because you don't know calculus, right? You don't know how the curve changes as the function progresses, right? We're just not sure using the empirical rule, okay? This is where the empirical rule kind of lets us down. The empirical rule is a really great approximation when we're looking at 1, 2, 3 standard deviations exactly. But now we're starting to see problems where we're asking these questions like this. He got more sleep than approximately what percent of students? Miguel didn't fall exactly 1 standard deviation above. So how can we answer these questions? Okay. Dun, da, 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 da. The standard normal curve. That's where this comes in, right? This is a whole section of notes. Notes 9 is called the standard normal curve, right? At least the notes section we are in right now. How do we determine percentages like this problem above if they do not follow the empirical rule? Okay. Well, we can standardize the normal curve we just drew by converting all of that raw data into z-scores. Okay. And you're like, well, I would never think to do that, Goldie. Why would I want to do that? Just wait. The magic is about to happen here. Let's take Miguel's class's data, right, with a mean of 7 and a standard deviation of 1.9. Let's standardize all of those values, okay? And remember, to standardize, we use the z-score. So we're going to take each of these values that I have on my normal curve. I'm going to subtract the mean, and I'm going to divide by the standard deviation. Okay? So like for the mean, right? If I take 7 minus 7 divided by 1.2, I get 0. I'm going to draw that on a new curve over to the side here. Okay, so I got 0 in the middle. And again, you're like, why are we doing this, Goldie? Just bear with me. We're only going to do this once to prove a point. Okay, you don't have to do this for every problem you're on. We're going to prove a point here. Okay, I love proving the points. Okay, let's take 8.2 now. If I take 8.2 and I subtract 7 and I divide by 1.2, I get 1. Okay, so I'm going to put 1 right here. Okay. And maybe you're already like, duh, I see the pattern, Goldie. Shush. Let's keep going. 9.4 minus 7. Divide by 1.2. What do you get? 2 is your answer. Okay. So 2, I'm going to put 2 right there. 10.6 minus 7 divided by 1.2 equals 3. I'm going to put 3 right there. Do you see the magic that is happening, right? And maybe you kind of expected it. Maybe this was obvious to you, but for a lot of us, it's not obvious, right? What do you notice? You notice the mean is in the middle at 0, and then you went 1, 2, 3 standard deviations out. What do you think is going to happen to the other side? Well, 5.8 is going to be -1 when you find the z-score. 4.6 is going to have a z-score of -2, and 3.4 is going to have a z-score of -3. Okay. And what you just drew, what we have right here off to the right here, okay, that curve is called the standard normal curve. And any set of data that you have that is normally distributed, right? Any set of normally distributed data can be standardized into the standard normal curve. So we just did sleep, right? We could have done the shoe sizes from earlier. We could have done Mallory's test scores from earlier, assuming it was normally distributed, right? I guess test scores aren't always normally distributed, but if they were, we could have done it, okay? Anything that's normally distributed, we can create the standard normal curve from it, okay? And again, the question is great, Goldie, why? Okay, this was fun and special, but what does this help me do? Well, if we have a standard curve that we can fit all data, no matter what it is, we can standardize it to this curve right here, 0, 1, 2, 3. We have a standard set of measurements we can then use to determine what percent of data falls above, below, or between specific z-scores that we might find, okay? And that's pretty special, okay? We use z-scores to help us answer questions like Miguel, right? What percent of students did Miguel get more sleep than, right? Those kinds of questions we need to answer by first finding their z-score and then looking at what percent of data fell below that z-score. And we can't use the empirical rule, but we can use our standard normal curve. All right, and that's pretty special. That is pretty special. So standard normal proportions. For any z-score, we can find the total area, or we say total percentage, or total proportion, right? We kind of use those words interchangeably. So you'll see it called area, you'll see it called percentage, and you might see it occasionally called proportion. Later on in the course, you'll see it called probability, okay? But all of these are going to be finding the same thing. Okay, it's the percentage of data below, above, or between z-scores. Okay, so let's say, like Miguel in that first example, I wanted to find the percent below a z-score, right? What percent was below Miguel's z-score of 0.8? Was it 0.8? 0.83. Miguel had a z-score of 0.83, and I wanted to know what percent was below that 0.83. Okay, so here is another example. Sorry, this isn't Miguel's example, but below a specific z-score, it could be anywhere. Visually, though, this is what you're trying to find. I shaded the area or the percentage that we're trying to find, whatever that z-score is. We would call this, wherever that z-score is in relation to our normal curve, okay? Could be below the mean like it is here, could be above the mean like Miguel was. That z-score could fall anywhere, but I want to find the percentage below it, okay? I would call that z-score an upper boundary, and that would be an actual value that I found. That would be a z-score. On the other side, my lower boundary is what I would call negative infinity, because remember, our normal distribution, our density curves, they go out forever, okay? They go to the x-axis and they go out forever in a theoretical sense, right? So that lower boundary is going to be negative infinity, okay? So that's percent below. I'm just trying to give you a visual for this right now. Okay. Now, if I'm looking percent above, zip percent, so that capital P is the notation I'm using, okay? Later on, this capital P is going to stand for probability. Okay. For right now, we're going to call it percentage, but it's just setting you up for success later on to call it a capital P now for probability. But we're not talking about probability yet, okay? So just bear with me, all right? So capital P, think about it percent. Percent of, and then these parentheses are just part of the notation, okay, that we're using. And then we're saying our z-score, this is z. So we are signaling that, hey, this is going to be a z-score. This number right here is a z-score. And now I want to know the percent above a z-score. So greater than this number. Okay. How many z-scores are above? What percentage of z-scores, what percent of my data are above this value? Okay. So visually, this is what we're looking at. Again, my z-score could fall anywhere. Okay. Anywhere at all. But I want to find the percent above it. Okay, so percent above, now that becomes my lower boundary, okay, because I'm looking at percent above. Remember, this is my x-axis, right? So this is my x-axis. So this would be my lower, and then my upper would technically be positive infinity now, okay, because I'm going on forever in the positive direction. All right, and then the last question would be percent between z-scores. Okay. So if I have two z-scores, I just call it number A and number B, but these are going to be two z-score values. What percent lie between those two z-scores? This is what it might look like. It could be symmetric. A lot of them are symmetric, but it might be unsymmetric. Okay. It might not be. When we're working with this empirical rule, we are very symmetric with a lot of our stuff. It was also not symmetric. Okay. Depends on the problem. We have lower boundary and upper boundary. They're both going to be numbers. So those are the three situations that we're going to look at, okay, for our standard normal proportions. Percentages, exciting stuff, right? Okay. So I say we can take any raw data being any observation, any data set, test score, shoe size, heights, weights, etc. We can take any of them, convert it to a z-score, and then we're going to use our calculator to actually find the exact percentage of data below, above, or between these values, okay? Now, what we're going to use for our calculator is something called normal CDF. And so we haven't seen the distribution side of things yet. We are going to be talking about a lot of the distributions that are going to be listed in your calculator. For right now, so if you look at your calculator, whatever it may be, you see the VARs button. Okay, so I'm using the TI-84. So the VARs button, right above the VARs button in a different color, you see the DISTR. Stands for distribution. So you have to press second VARs, and you're going to see all the distributions pop up. Normal, inverse norm, TCDF, TPDF, all of that exciting stuff, right? For us, right now, the only one we are going to use is called normal CDF, and that's going to be listed as number 2. There's a normal PDF. Notice the PDF is 1 and the CDF is 2. I'll explain more about those differences when we get into probability a little bit more, but we in AP statistics do not use normal PDF. Okay? We only use normal CDF. So just stay with it. Normal CDF. On those calculators, when you press normal CDF, you're going to get this menu pop up. Okay? Now, the lower and upper stand for the z-scores that you're going to use. Okay, so depending on what the problem is asking, above, below, or between. If you are looking for below a value, your lower is going to be negative infinity, and your upper is going to be that z-score. Okay, if you're looking for above a value, it's vice versa with a positive infinity. Now, to put infinity in your calculator, you can do just like a really long, like you can put like that in, right? Now, to be politically, mathematically correct, okay, the way we put infinity in our calculator is we do 1, we put in the 1, and then we follow it by the times 10 to the value of whatever, in this case 99. So this would be this is like 1 times 10 to the 99, right? Which is really large. Now, in order to get this on your calculator, that's where the E comes in. Okay, for scientific notation. So that is on my calculator here, which is going to be on probably most of your calculators. That's going to be right above, there's a comma button. I probably should turn on my emulator, and right above that comma button is that EE. You press second and then press that comma button, and that's going to get this E to pop up, and then 99. Okay. Or if you're looking at negative infinity, you just put the negative symbol. Remember the negative symbol? If you can see that on my screen, that's right here. Not the subtraction symbol. Subtraction and negative are 2 different buttons on your calculator. And you'll get an error if you try to use one instead of the other. Okay? So, or for now, until you ask your teacher if you're having trouble, you can just put in a really large number or really large negative number. Okay, so lower and upper. We'll do a couple of examples here in a moment to show you what I mean by that. And then when we talk about our mean and standard deviation, we're looking at the standard normal distribution. So because we're using z-scores, okay, and we find z-scores, and we're putting in z-scores as our lower and upper boundary, we want the mean and standard deviation to be that of the standard normal distribution, which means our mean is going to be 0 and our standard deviation is going to be 1 every time. Okay, mean 0, standard deviation 1. Okay, please be careful that you do not accidentally put in the raw data there. Okay, the data that you're given in the problem. What we're going to do in our class, we are going to find our z-scores, and then we're going to put our z-scores for the lower and upper boundaries. And when we use z-scores in normal CDF, we have to use 0 and 1 from the standard normal curve. Okay. There's other ways you can do it that we'll talk about next a little bit later on, probably in the next video. But for right now, the standard normal curve, 0 and 1 for mean and standard deviation. Okay, that's a lot of setup. Let's get into a few examples. This is actually, I think, how we're ending the notes for today. We're going to continue it in the next set of notes. But for today, we're just going to end with a few calculator examples of how we find these proportions or these percentages. Okay. So let's say what percent of data is below a z-score of 0.54. So notice this is almost very similar to the Miguel example where we found his z-score of 0.83 and then we wanted to know what percent was below him. So in other words, he was better than, what percentage of his classmates when it came to sleep. Okay, very similar. And we're going to tie in real world examples with problems like this next in the next set of notes. Okay? For right now, I just want to get the calculator down so we understand the calculator. So what percent of data is below a z-score of 0.54? First, let's write the notation in terms of the problem that we're trying to find. As an inequality, we are trying to find the percent of data that is below a z-score of 0.54. So this is what that problem is going to look like. We have P, and then in parentheses, we have Z less than 0.54. Okay? Saying what percent of z-scores are below 0.54. Now let's draw this curve and shade the area. Now when I say draw the curve, we're working with z-scores. So we're going to draw the standard normal curve, which is centered at 0, 1, 2, 3 standard deviations out on either side. Okay. And then 0.54 is going to be approximately, it's near 0.5, right? So it's right between 0 and 1 on the x-axis. And we want to find the percent below. So we're going to shade all of the region below that value. Okay. Now, what do you know about this percentage? Well, just based on the empirical rule, you know that this is going to be above 50%, right? Because I guess I'm using red here. This is 50% right here. So it's a little bit above 50% right here. Oh, sorry. It's red. Red on red never works, right? But what percent is it exactly? Well, that's when we use our calculator. So our calculator here, my lower boundary is here, and my upper boundary is going to be this 0.54. Okay. Now, I say my lower boundary, I say it's right here. In theory, it's right there, right? But it goes on forever. So that's going to be negative infinity. Okay. So I'm going to put negative infinity in my calculator. Again, this is normal CDF. Normal CDF. Oh, I don't think that's writing on the screen. Technology, I tell you. Normal CDF. Let's see. There we go. Who needs it? Normal CDF. Go to your normal CDF screen. Lower boundary is negative infinity. Upper boundary is going to be that 0.54. We're working with z-scores. So your mean is 0, standard deviation is 1. You do that and you press calculate, and you're going to get your percentage, right? Yeah, which is what I expect. Now it's a decimal. In AP Stat, most of the time you're going to be working with decimals, and that's perfect, right? 0.705, that's your answer. Signed, deal is done, okay? If you want to report that as 70.5%, do what your heart desires, right? You're the mathematician here. Do what your heart desires. If you want to say, 70.5% is where my heart's at, call it 70.5%. Just know that you might see it both ways, okay? But that's on par with what we were thinking, right? Because we know that 50% is less than 0, and we know that less than 1, we know that this is 84%, right? So about 70.5%, that's pretty expected, okay? That's on par with what we know with our empirical rule, all right? Okay. 2 more examples here. Next example is above a z-score. What percent of data is above a z-score of 0.17? Okay. So our inequality now, percent z-scores above 0.17. Draw the curve, shade the area. 0.17 is right about here, right? So what do I know? Again, I know that this, from 0 onward, I know that this is 50%. So this percentage is probably like a little less than 50%, right? Something like that. Let's find it using our calculator. So go to your normal CDF screen, normal CDF. Sorry, that's supposed to be an N. Who writes N's like that? God, gravy. Calculate the percent using those, put in those 4 values, right? So what's your lower, what's your upper here? With z-scores, your lower is this right here. Remember, you're working with an x-axis, right? So your lower is here, your upper is here. Okay, so your lower is now 0.17. Your upper is now positive infinity. Okay, so lower to upper. All right, mean 0, standard deviation 1. The percent, perfect, just less than 50%, 0.433. If you want to do the percent, right, that's fine. That's the percent of data above that z-score. Okay. Now, if you do the percent, normally we do 2 decimal places at least on those percentages. On the free response, it really wouldn't make too much of a difference on the AP exam. But on the multiple choice, you want to try to keep usually at least 4 significant figures, especially if you find this value and then you use the value in another calculation. You want to keep those significant figures long to avoid any round off errors in the multiple choice questions. On the free response, it usually doesn't matter as long as you're showing your work. If you round like to 3 decimal places, usually the grader can follow and you'll get all your points. But for good practice, you want to try to keep your significant figures to at least 3 or 4. Okay? All right, I think this is the last problem. What percent of data lies between a z-score of negative 1.64 and z equals 2.33? Okay, so not symmetric. Let's write our inequality though. Okay, so between those two z-scores, that's what our inequality is going to look like. Let's draw and shade the area. Okay, so I got negative 1.64 is right about here, and 2.33 is right about here. Okay, so that's where I draw in those boundaries and then shade the area in between. And actually, students do really well with this because there's a clear number for the lower boundary and a clear number for the upper boundary now. The lower is negative 1.64. The upper is 2.33. I'm still working on my standard normal because I'm working with z-scores. Okay? Just remember, whenever you're working with z-scores, you're working with a standard normal curve. So your mean is always 0. Your standard deviation is always 1 for that. And then you click enter, the percentage 0.940, rounding. Or 94% if you want to write it as a percentage. Okay. And that does bring us to the end of our video. Look at that. So I thank you guys so much for following along. There's the last answer there for you before I click out too quickly. But I want to thank you guys for following along with me and watching this video. In the next video, that's going to be our last video in this unit actually, and talking about the normal distribution again. We're going to take what we just learned here, we're going to apply it to some real world problems, and then we're going to talk about one more type of calculation you're going to be asked to do with the normal distribution. So we got one more exciting set of notes. Make sure to stay tuned for. But until then, if you have liked this video, please hit the like button and subscribe to my YouTube channel for more great AP Stat content. Otherwise, I will see you in the next video. Thank you so much.